want to do a couple questions that relate to long division, and then kind of parlay that over into synthetic division, and then talk about some theorems that arise due to our result of that division. Okay, so that's the plan for today. First things first, you're going to see questions kind of written this way. Obviously, that tells us that x minus 1 is the divisor. So x minus 1 goes on the outside. Now, what is unique about this problem that we should pay attention to that the other ones from yesterday did not involve or did not include? Okay, good. So when we write this, if you write it as x minus 1, and then underneath the division, you have 2x cubed minus 2x minus 3. Okay, don't write all that yet. If I'm thinking about what I need to multiply by x minus 1 to get this 2x cubed, what would it be? 2x squared. Okay? Now here's the idea. If I multiply out, okay, and basically distribute to x minus 1, I get 2x cubed minus then 2x squared, right? Notice how, obviously, those line up, okay? But are those like terms there? No. If you forget the placeholder, it's not impossible. You can still do the work without the placeholder here, okay? You just have to realize that, I'm not subtracting anything from the x, and I'm not subtracting anything from the 2x squared. So it's going to be minus 2x squared minus 2x minus 3 that I bring down. Does that make sense? You just have to be leery of that and pay attention to that. If you're not paying attention to that, you can obviously miss the problem. So my suggestion, just to be safe, is to add that placeholder of 0x squared. And then that will allow things to line up so that they are like terms. So now, it's still the same 2x squared that we're going to put up there. Multiply out gives me 2x cubed minus 2x squared. Told you yesterday I like to negate everything, multiply that row by a negative 1, and then add straight down. So that's going to give me those to go away. Gives me this 2x squared. Oh, this should be, I don't know why I put a cube right there. That's a first, sorry. Minus 2x minus 3. Does that make sense? Okay. Ultimately, you bring down everything from the original problem that you did not use in that first step of the algorithm. Now you have to ask yourself, what do I need to multiply by so that I can get this 2x squared right there? We're going to multiply x minus 1 by to get that 2x squared. 2x. So multiply by 2x. So 2x times x gives me 2x squared. 2x times negative 1 gives me negative 2x. Okay. I'm going to negate everything and add straight down. So those wipe away. Those wipe away. And now it leaves me a remainder of 3, right? Yep. Now we know that's our remainder because that's a variable of x with an exponent of 0. And when that exponent is less than that exponent, which that exponent is a 1 right now, that's when the division algorithm tells you to stop. Okay? So that's my remainder of negative 3. So I'm going to write plus negative 3 over my divisor of x minus 1. And now think about this. It's the same thing with any type of division that we do. If I had like 42 and 7 here, that would give me 6, right? And the idea is that the 6 times the 7 should give me the 42, right? Okay. Even if I had, let's go, let's do it this way. Go 6 And let's go 40 to 40, let's say 45. Okay, so that's going to be a 7, right? It's going to be 42, remainder of 3, right? So this ends up being 7.5, correct? Well, 7.5. So, or if you want to write a 7.5, or 7 plus 1/2, that thing there times my 6 will give me another 45. So does it make sense that this here, I didn't highlight. Does it make sense that this thing here times the x minus 1
Again, teachers and students, please remain in your second period classes. There was no transition for walkout time today. Second period will now end at 10:24. When that bell rings, you can proceed to third period. Thank you.
Did we already know that? I don't know yet. So we'll take this blue thing, we'll take this quotient plus our remainder over our divisor, and if we multiply it by x minus 1, shouldn't it give me that thing right there? Does that make sense? So the idea, when they ask you the formats for your answers, they're going to say, write it as P over x divided by D over x is equal to your quotient of x plus your remainder of x divided by your divisor of x. So each one of these is a polynomial, right? P of x, D of x, R of x, Q of x. So what they're saying then is 2x cubed minus 2x minus 3. That's your polynomial, P. Your divisor was x minus 1. That is equivalent to your quotient, which was 2x squared plus 2x. Okay? That's your quotient. Plus then your remainder of negative 3 over your divisor of x minus 1. Those two things are equivalent. If you would take this and try to add it together so that you get a common denominator, so I have the x minus 1 being my common denominator, everything's going to merge together as that fraction, 2x cubed minus 2x minus 3 over x minus 1. Okay? An alternative way of writing it is to say P of x is equal to your quotient of x times your divisor of x plus your remainder of x. And the way that we get this rule here is that we started with this one and just multiply everything by that d of x. Okay, to get rid of the fraction. So P of x is the 2x cubed minus 2x minus 3. Q of x, we said that was a 2x squared plus 2x. Your divisor, x minus 1, plus your remainder of negative 3. If you were to multiply that right-hand side out, it gives you 2x cubed minus 2x minus 3. Here's the benefit of these things. Here's the benefit of these things in this process is that there will be times where that remainder is 0. Does that make sense? And then this would be now a quadratic times a linear function to develop this cubic. So it gives us a way of breaking down this cubic so that we can factor it a little bit easier. Okay? So our hope is that eventually, as we start doing these more and more problems, that remainder turns into a 0. Okay? And that's going to be a very, very nice thing for us. Okay? Now, I want to do the same thing, but you guys were introduced to synthetic division last year, correct?
Yeah.
Okay? So synthetic division, if I take the exact same problem, did we talk yesterday about when we're doing this division, right here, this divisor
for a lot of the questions we're doing, this divisor is going to be a linear divisor, x to the first. But it could be x squared, it could be x, it could be anything. Does it make sense? Okay, it can be any power. And the algorithm is going to be the same thing. When we do synthetic division, folks, it's going to be, synthetic division limits us to the things that we're allowed to divide by. Let me try to find a nice place here to work. All right. So I want to do the same problem, but I want to work with synthetic division. So synthetic division is only going to allow us to work when that is a x to the first. Okay? If it was x squared minus 1 or whatever, we're not going to be able to use synthetic division in the manner that we learn it here. Okay? You guys remember synthetic division kind of set up? Has this little box on the left.
Yeah, I remember.
You put this line down here. Okay. What goes, you guys remember what goes in this box? It's not negative 1. It's positive 1.
Oh,
Okay.
I'm a failure.
So what goes in the box is the answer to the equation x minus 1 equals 0. Okay? Or, in general, x minus c equals 0, which is obviously then x equals c, right? C is what goes in that box. Okay? The next thing, we construct a row here of coefficients. And the coefficients are the coefficients that are in our original P of x, right? Okay. Now this is where we have to be very aware and vigilant of how this thing is structured. We are missing an x squared term, right? You have to have that placeholder. We're talking about when you do long division, if you're thinking about what you're really doing long division, if you don't have a placeholder, you can maybe get away with it. Synthetic division, if you don't have those placeholders, you're not going to get away with arriving at the right answer. Okay? So you need to be paying attention to that. So, that's the setup. Okay? Now, as we do synthetic division, the idea is that it should take us, or it should give us a process that is a little bit cleaner, a little bit more concise, a little bit quicker, but we also lose some detail. Okay? We took all the variable components away, and we just have to think about some logical ideas when we're done. Okay? To kind of tell us what our numbers at the end really mean to us. So if you remember, the first step of synthetic division is to take this first coefficient and you just bring it straight down. You don't do anything with it. Bring it straight down. You're then going to take this number that's in the box and you do what with that 2? Multiply it. And when you multiply, that term goes right there. So 1 times 2 gives me that 2. Okay? You are then going to add straight down. Gives you 2 again, right? And then you just repeat the algorithm. You're going to take this 1, multiply it by that 2, and that result then goes there. And then you add straight down. And then you're going to take that 1 times that 0, and that result goes right there, and you add straight down, right? I've always, on that last term, that last, usually they're going to be, I don't want to say it, that last real number, okay? They might be fractions, they might be integers, they might be, at some point, we'll work with complex numbers like a plus bi and these things. But that last object, I always put a line to the left, vertical line to the left of it, because it separates my quotient and my remainder. Okay? The idea here is that this is your Q of x. This here is your remainder, R of x. Okay? Now, here's where at the beginning of the problem I said we lose some detail. And we have to be aware of that so when we're done, we know what this stuff here means to us. We took an x cubed. So let's just take 2x cubed.
and we divide it by x minus 1, or x to the first, right? If you divide x cubed by x, what's that turn into? 2x squared, right? So when you divide a cubic by a linear, if you remember, the idea is I get 2x to the third times x to the negative 1, and that's really 2x to the third minus 1, right? So when I divide by the same base, I subtract the exponents, correct? Well, that means when I take a cubic and divide by an x to the first, this here, this 2, is going to be x to the what? X to the second. This was x cubed. This is x to the second. And that's going to be consistent every time we do synthetic division, is that your quotient line is going to be a depreciated polynomial of degree 1, meaning that if I started with a degree 12, then that row would be degree 11. If I started with degree 54, then the quotient row would be degree 53. Does that make sense? It's always one less because of what you're dividing by. You're dividing by a linear term. So, if that's x squared, this needs to be x to the first. This would be x to the 0. That's just my constant. So then I can rewrite this as 2x squared plus 2x, and then minus my remainder over my divisor. And that's writing this thing as q of x plus r of x over d of x. Okay? That's one way of writing the answer. And the other way, obviously, is to say, well, p of x then is q of x times d of x plus your remainder. My quotient is 2x squared plus 2x times x minus 1 plus negative 3. What we're going to find out, guys, is that route there is actually the preferred. When we start actually applying this to what we're trying to do, we're trying to eventually find all the zeros of a polynomial. That technique right there is going to be a benefit to us, because when that minus 3 actually becomes 0, if that were a 0 there, that would tell me x minus 1 is a factor, so positive 1 is a 0, or an x-intercept of my graph. Okay? So that's something to think about. Now, there's a relationship that exists here that will always be true, and it has to do, if we have time tomorrow, we'll prove this, but it has to do with this remainder, okay? If I were to ask you to take this as p of x, okay, and I ask you to find p of 1, okay, so let me just come over here. P of x was 2x cubed minus 2x minus 3, is that right? Minus 3, okay. And I asked you to find p of 1. The way we know about how to do that right now is just to go find the x and replace with 1, right? So we get 2 times 1 cubed minus 2 times 1 minus 3. So that means p of 1 is equal to 2 minus 2 minus 3. Is p of 1 negative 3? That's the what, Blaze?
The remainder.
That's the remainder. Okay? That's the remainder when you divide it by that 1, right? We do synthetic division with that 1. That's called the remainder theorem. Okay, so I'll put this over here for you. We'll come back up and do this other example here in a little bit as well. But the remainder theorem states for us that if the polynomial p of x is divided by x minus c, so that's a linear term, okay, then the remainder of that is going to be the same value p of c. Okay? Now, the benefit of knowing this is, let's say I'm asking to evaluate some polynomial at some number, okay, maybe some obscure number or very large, very small number, something like that.
and you don't want to use your substitution technique. You don't have to, okay? Because you can arrive at the same answer by using synthetic division and linking my remainder to that. Okay? This happens to help us eventually when that remainder becomes 0. Okay, and we'll talk about that. What's this? Let's say if P of C, if the remainder, if I evaluate at C and I get 0 back, remember C is an X value, right? That's my remainder. Well, that means I evaluated my polynomial at C, got a remainder of 0, got 0 back for this evaluation. That's an output. That's a Y value. So if I have the ordered pair C comma 0, isn't that an X-intercept if the Y value is 0? Does that make sense? So that's what we're looking for. That link right there is going to help us realize that when our remainder is 0 in the synthetic division, that means if you evaluate your function at the C value that you used and got 0 back, I must admit that you're now looking at an X-intercept. Okay. So let's do an example. The example we do here won't give me a 0 right away. We'll get to one eventually that provides a 0, but let's do, where did it go? So 2x cubed minus 7x squared plus 5. And we're going to divide that by, I said x minus 3. Okay. So setting up the synthetic division. What should go in the box?
3.
3 goes in the box. We'll go 2, -7, 0, 5. Okay. Bring my 2 down. Multiply gives me 6.
-1 is 1. Bring down 3. -8. Remainder is -4.
Okay. So, writing my polynomial then, if this was x cubed, what's this?
X squared.
X squared. So this quotient row here, q of x, okay, q of x is going to equal 2x squared minus x minus 3, right? Okay. If I'm going to add my remainder to that, I will then say plus -4 over x minus 3, right? Okay. Or, if you want, you can think 2x squared minus x minus 3 times x minus 3. So my quotient times my divisor plus my remainder should equal my original polynomial. Should equal that thing right there. If we were to take, you can do it, you can use GeoGebra, you can do a quick Google search for some computer algebra solving systems that allow you to FOIL it out, add it together, and it'll give you 2x cubed minus 7x squared plus 5. Okay? So here's my question. If I were to ask you, well, if this is my original polynomial, or that right there is my original polynomial, and I ask you to evaluate and find P of 3, you can plug 3 in for all these x's, right?
Yeah.
And evaluate. So let's try to do that. What's 3 cubed? 3 times 3 times 3? 27 times 2 is 54, right? What's 3 squared? 3 squared is 9. Or times 7 is 63. And then add your 5, right? Well, what's 59? 59 minus 63? -4, right? So when I ask if P of 3 is equal to -4, isn't that the same thing as what the remainder was? Yes. And that will be the case all the time. Okay? So our goal is to eventually, when I say what's P of 3, if it ends up being 0, that tells me 3 is an x-intercept. Okay? Because the y value then is, because when I'm asking what P of 3 is, I'm asking you to figure out what is the y value when x is 3. But when this is 0 through synthetic division, we'd be saying your y value is 0 at that x. So it gives us an x-intercept. Okay. So that gets us down to, we talked about the remainder theorem. Oh, we got 9 minutes. We're going to factor theorem. Okay? And this is really what's going to, the remainder theorem along the factor theorem is going to allow us to start breaking these larger polynomials, higher degree polynomials, down into their linear factors. Okay? A factor theorem is a biconditional. It says if and only if here. Okay? So what I'm going to write is if C is a 0, then x minus C is a factor of P of x. So when I see if and only if, basically what I do is I wipe it out. I put the word then there, and then I write the word out front if. Does that make sense? And that's all I got here at that red statement. But the word if and only if tells me, or the phrase if and only if tells me, once I write this one, I can actually find the converse of it, which means takes the then part and flips it with the if part. So I'm going to do that. I'm going to write if x minus C is a factor of P of x, then C is a 0. Those are the two statements that are encapsulated inside this original statement in that blue box. Okay? You can read, whenever you see the phrase if and only if, you can use that statement two directions, forwards and backwards. Okay? So if I have a 0C, then I know that I can work backwards and find x minus c as a factor of the polynomial. Make sense? So I told you that we have a quadratic and the 0 is 5. Let's say 5 and 2. Then you know that the factors that 5 and 2 came from were x minus 5 and x minus 2. Does that make sense? Okay? So we've done that. We've worked that way backwards before. That's what this is saying. Okay? And the blue one is saying, well, if I factor things down to x plus 5 and x plus 2, then I know that x minus c is a factor of P of x, then the 5 and the 2 are zeros of P of x. Okay? That allows us then to start factoring some of these polynomials. So I'm going to say, like, our goal eventually will be to take this thing here and have absolutely no knowledge about the factors of that polynomial. Okay? And we will work through breaking that down to 3 linear factors. Okay? 3 x plus something, x plus something, x plus something. Okay? Right now, we don't know how to get the ball rolling, so what they will do is they will tell you to try some value first. Okay? So right here, they're trying to see if P of 1 will work. So they say, show that P of 1 equals 0. Well, that means I can either, if this is P, I can either put 1 in here and evaluate, or I can do synthetic division. Now, here's why synthetic division is a better route. If I just plug in 1 here, all it's going to tell me is 1 cubed minus 7 times 1 plus 6. Yes, that does work. I do get a 0. It means x minus 1 is a factor, but it doesn't leave me with the other factors. Does that make sense? But synthetic division, if I go x cubed, which is a coefficient of 1, x squared's coefficient is 0,
X's coefficient is -7, and my 6. I put in this box, okay, I want to put 1 in, right? Okay, it's the C value, and this is P of C here. I bring my 1 down, multiply, put 1 there, add down, multiply, 1 down, -6, multiply, -6, add down, gives me 0, right? Okay, well, that is telling me right there, that 0 is telling me the same thing that worked right there when I evaluated that way, okay? So it tells me the same thing, that this thing here, just like this, is if x minus c is a factor of p of x and c is a 0, and if c is a 0, then x minus c is a factor, so x minus c here is a factor. So it tells me x minus 1 is a factor, just like this did, right? And what's nice is that this row here is the quotient when I divide by x minus 1. Does that make sense? I have no remainder to add here, so when I go x squared, this was x cubed, this becomes x squared, I go x squared plus x minus 6. Does that make sense? Okay. Now, think about this. Is that something that we have tools to factor? Do you know how to factor x squared plus x minus 6?
I think so.
How? X plus 3, x minus 2, right? So this thing here, this x cubed minus 7x plus 6, okay, is what we started with. We can rewrite it now that way. We can factor it that way. Why do I want to factor it that way? Because our goal is to graph it, right? At x cubed right now, I know the behavior. It's got a positive 6 at the end. I know the y-intercept is 0, 6. And now I know I have an x-intercept of 1, an x-intercept of -3, and an x-intercept of positive 2. Does that make sense? Yeah. Okay. Now, here's the thing. We did not know at the onset that value of 1. They had to give that to us, right? They had to start us off with that. Okay. Over the next couple of days, we'll learn a process. Hopefully we'll go through the proof of why it works. We'll learn a process of generating potential p-values that would give us a 0. Okay? And remember the P over Q stuff, right? Okay. Okay. You remember take the factors of 6 and the factors of the first term 1 and the x cubed coefficient, and then dividing them and creating a list of potential zeros. We'll do that later. Might start tomorrow. Depends on the time that we have. But that's where we're getting to. We're going to get to. I should be able to eventually, maybe in a week or so, give you any polynomial of any degree, and if it is factorable across the real numbers, you should be able to do that. Okay, find all the zeros.
I don't use that method because my old math teacher said it was reductive.